All right, welcome back. And we are about halfway through our lecture on Chapter 19. So this is our second video for Chapter 19. And we're starting with the concept of Gibbs free energy. What makes free about Gibbs free energy is that it's the amount of energy that is free to do useful work. Right? It's analogous to potential energy and related to spontaneity. Now we have an equation. So Gibbs free energy has a very logical symbol of G for Gibbs free energy, and it's related to enthalpy, temperature, and entropy. Okay, and this is all done at constant temperature and pressure. Okay, so when I want to talk about a change in Gibbs free energy, all I have to do is put a bunch of deltas in there. Delta G equals delta H minus T delta S. Okay, and this is all related to measurements on the system itself. Measurements on the system. Okay. Right. It's important to keep that in mind, is that we're focusing on the system with this. Okay. So the reason that Gibbs free energy is even a thing is that there are a number of chemical processes out there in the wide universe that are spontaneous. They happen of their own accord, but have a non-spontaneous change in entropy. And so when scientists started to put all this stuff together, they were like, wait a minute, this doesn't work with our current set of definitions. So the scientist, mathematician, William Gibbs, hence the name Gibbs free energy, came up with a new state function that was able to describe processes that were spontaneous but had a negative change in entropy. Okay, so with this equation, when the entropy change is positive, delta G is negative. Okay, so when that is the case, we have a spontaneous process. Right? So negative delta G equals spontaneous. Right? A positive delta G, as you might suspect, is non-spontaneous. And when delta G equals 0, and here's a new idea that we were able to do with this particular idea, boy, that was a wonderfully redundant statement, is that at delta G equals 0, now we can talk about things that are at equilibrium. Okay, so we can get a sense of whether this thing is going to automatically just run on its own, whether it's not going to run on its own, or whether it's at an equilibrium state. Right? Now, with this wonderful equation, with delta G, that's a terrible delta. Let's try again, Jake. Delta G equals delta H minus T delta S. We can talk about the effect of the signs of enthalpy, entropy, and temperature. Really not temperature, because temperature's on the Kelvin scale. But we can talk about the signs on entropy and enthalpy and how it affects spontaneity. Okay, so just based on those values, whether they're positive or negative for H or S, I can tell whether or not delta G is going to be spontaneous. Okay, so looking at the signs of delta H and delta S. Okay, so if delta H is negative and if entropy is positive, that means that delta G is negative at all temperatures. Right? It really doesn't matter what I plug in for my temperature. This will come out to be a negative, some sort of value, but it's always if delta S is positive, then that will end up being a positive value, and I'll have a negative minus something, minus a positive, still equals negative, right? So delta G will be negative at all temperatures, regardless of what the temperature is, okay? And I apologize for being stuttery. So if I take a look at a different scenario, if delta G equals delta H minus T delta S, if H is positive and delta S is negative, that is going to cause delta G to be positive at all temperatures. Okay, so if delta G is negative, we're spontaneous. If delta G is positive, we're non-spontaneous. Okay, so doesn't matter what temperature I plug in, because we're on the Kelvin scale, so there's no negative temperatures. Doesn't matter what temperature I plug in, if H is positive, S is negative, G will be positive at all temperatures and non-spontaneous. So let's look at a different situation. What if they're both negative? So if delta G equals delta H minus T delta S, if H is negative and S is negative, then now temperature matters. Delta G depends on temperature. Okay, so if my temperature's low, I'm going to get a negative delta G. If my temperature's high, I'm going to get a positive delta G. Okay, so negative at low temperature, positive at high temperature. All right, now there's actually a really simple way to figure this out. Okay, if your signs are negative, if both the signs are negative, think about that in terms of temperature level. So if it's a negative number, we're thinking about something that's low, right? So we can figure the signs on delta H and delta S will tell us what temperature will give us a negative delta G, right? So low temperatures, negative values are low things, okay? So it's just one way to not have to rote memorize these situations. So conversely, if I have if these are both positive, guess what? Delta G is negative at high temperature this time and positive at low. Okay, again, same idea. Positive things are large in sort of a very general sense, right? So when the signs are the same, the sign itself will tell you whether delta G will be negative at high temperatures or low temperatures. Okay. But the point, the takeaway from this is that if the signs are opposite, as they are up here, delta G does not depend on temperature at all. It doesn't matter what temperature it is. Go with the value of S. Right? Right? So if S is positive, that's a spontaneous process. And if the signs are opposite, positive S, negative H, that'll result in a negative delta G at all temperatures. If the signs are opposite and the sign on S is a non-spontaneous process, that should say non-spontaneous, then the non-spontaneous process will be that way at all temperatures. Okay? If your signs are the same, let the signs tell you whether it's low temperature or high temperature for a negative value for delta G. Okay? So let's do a little bit of evaluation here. All right, so you should be able to look at, very much like dealing with S, given enough information, you can go straight from a chemical equation to determining whether or not something will be spontaneous. So let's look at an example where we have the equation 2NH4NO3 solid decomposes to nitrogen gas, water, vapor, and oxygen gas. And we're given a delta H, standard delta H, of negative 236 kilojoules per mole. Okay. So let's look at what we have. So over here on the left-hand side, I have a solid. And over here on the right-hand side, I have 2, 4, 6, 7 moles of gas. Okay. So what is the value of S? Right? So when I go from a solid to making gas, I'm increasing my microstates, right? So S is going to be positive, or we can say greater than 0. Okay? That means S is positive, delta H is negative, minus T delta S. So S is positive, H is negative. We have a spontaneous process. Okay? Just given the information for a particular equation, right? Just looking at going from solid to a bunch of moles of gas, I can tell that that's going to be a positive delta S. Delta S, right? And this will be spontaneous at all temperatures. Right? Because my signs for H and S are opposite. Okay? And I let the sign for S tell me that it is a spontaneous process. All right, let's do another example here. If I have iodine gas becoming 2I gas, delta H, we don't know. Okay, so what do we know about what's going on here? So we have more moles of gas in the products, so we know that delta S is going to be greater than 0, so positive, right? We also know that we've got an iodine molecule, a diatomic molecule, breaking apart to becoming 2 iodine atoms in the gas phase. So, bonds breaking takes energy to input. Right? No new bonds are formed, so that means that delta H is going to be positive. We have to put energy in, right? So if I have my equation delta H minus T delta S. So S is positive, H is positive. So that means that delta G, spontaneous at high temperatures, non-spontaneous at low temperatures. Okay? And again, I let the signs, right, they're positive signs, so positive things are large. So spontaneous at high temperatures, non-spontaneous at low temperatures. So we can do quite a bit just from a very little bit of information. Okay? Right? So we already talked about entropy in terms of state changes, but Gibbs free energy is a little bit different with state changes. So things to remember or keep in mind about state changes and Gibbs free energy. All right. So at the melting point, what is actually happening while melting is happening is an equilibrium. Okay, so during that phase change, that change of state, I have an equilibrium between my solid state and my liquid state. That means that at that state change, delta G equals 0. Okay, because delta G is 0 at equilibrium. So at the boiling point, I have a equilibrium again between solid and gas, or liquid and gas, right? So equilibrium means that delta G equals 0. Okay? So keeping that in mind. So entropy at a phase change is not a 0 value. Remember, we can calculate that from enthalpy and temperature of the transition. But for delta G equals 0 at phase changes. Okay? Standard Gibbs. We always keep coming back to this standard thing, right? So we talked about standard enthalpy and standard entropy, and guess what? Delta G standard equals delta H standard minus T delta S standard. And take a wild guess what this is going to look like. Sum of the products, delta G formation for the products, minus sum and reactants, delta G of formation for the reactants. Okay. Delta G of formation is just the standard free energy of formation. Okay. And again, just like with every time that we do these types of problems, these are in tables. These are tabulated values. Okay. So let's do an example. 2 ways to calculate the standard delta G standard. Right. So here is our example, and I'm going to change up the ink color because I'm tired of it. So we have 2 NO gas. Apparently I like this nitrous oxide formation. equation. And we get 2NO2. And this happens at 298 Kelvin. Right? Delta H standard is negative 114.1 kilojoules, and my change in entropy standard negative 146.5 joules per Kelvin. So I can take that, if I have those values, I can just plug them straight into this equation. Right? So delta G standard equals negative 114.1 kilojoules minus 298 Kelvin times negative 0.146.5 kilojoules, right? Make sure that your units match. Joules per Kelvin. Right? And when we do that calculation, we come out to have delta G standard of negative 770.4 kilojoules. Okay? So let's say that we don't have delta H or delta S. Right? So let's approach that problem again and use the free energy of formations. Delta G of formations. So for NO, we find that that has a value of 86.55 kilojoules per mole. O2 is 0 because the delta G of formation for a standard state is 0. And we have NO2, we have a delta G for that of 51.31. Okay, so delta G naught of the reaction, products minus reactants. Right? Just like we've done quite a bit before. So I'm going to say delta G of reaction equals 2 times G naught of the NO2 minus 2 times the delta G for NO plus the delta G formation for O2. So we get 2 times 51.31 kilojoules minus 2 times 86.55 kilojoules plus 0. And when we run that bit of arithmetic, we find out that this comes out to be 70.5 kilojoules. So almost exactly the same value we got up here of 70.4, but from a completely different way of calculating this. And it's a negative delta G, so this is a spontaneous reaction. Right? All right, now the next thing in my notes talks about coupled reactions, and I think I'm going to skip over that for the sake of trying to keep this a little bit shorter, and I don't think that that is anything that you need to worry about as far as mastering or what's in the textbook, but suffice to say that if you have a chemical reaction that is non-spontaneous on its own, you can actually couple it with a spontaneous reaction, and when you combine those reactions, you end up with a spontaneous reaction. Okay, a lot of metallurgical processes do this, where they couple reactions and so that they end up with a favorable delta G, so that the reaction will work. All right. So the last thing that we need to talk about in our chapter 19 is delta G and the equilibrium constant. Because we've already seen that at equilibrium, delta G has a particular value, okay? And we're going to start by talking about delta G under non-standard conditions, okay? Now, standard conditions are simply when everything, when all components are at 1 molar. All right? So delta G at non-standard conditions looks like this. Not non-conditions. Non-standard conditions. Non-standard. Okay. Looks like this. Delta G equals delta G naught, or delta G standard, plus RT natural log of Q. All right? Standard delta G. We have the gas constant, (8.314 joules per mole Kelvin). Temperature in kelvins, and then Q is the reaction quotient. Right? And that thing is calculated like an equilibrium expression. Right? Remember from chapter 15. Right? So we're starting to tie things together. We did all that work with equilibrium in the last two chapters, chapters 15 and 16, or 16 and 17. And now here we are in chapter 19, and we're starting to tie the concepts of equilibrium to new things. So, to illustrate how this relationship kind of works. So with this expression, if all components are at 1 molar, then Q equals 1, and natural log of Q will equal 0, resulting in delta G equaling standard delta G. Right? So if we're at standard conditions, this still works and still gives us the right answer. Okay? That delta G is at standard delta G. Okay? So the other interesting thing about this is that should be an A, at equilibrium, Q equals K, right? Remember that from chapter 15? So we can substitute it into the equation. And we get delta G equals standard delta G plus RT natural log of K. Right? That is the equilibrium constant. Right? And then the next thing to remember is that at equilibrium, delta G equals 0. So we're going to rearrange the equation, and what we get is at equilibrium, delta G standard equals negative RT natural log of K. Okay, so two important equations, right? So two important equations. This one, where we're looking at delta G at non-standard conditions. Okay, and the other important one is this one, delta G at equilibrium. Right. So let's look at some examples of how we can utilize this information. All right. So, example. So here's the type of problem that we could apply this to. The Haber process is used to manufacture ammonia. Manufacture ammonia. And a lot of my personal PhD work was about this particular process. And the reaction looks like this, and I've used this one in class quite a few times. Plus 3H2. And it's an equilibrium process making ammonia. And the delta G for that, the standard delta G, is known to be minus 33.3 kilojoules at 25 degrees Celsius. Okay, so at 25 degrees Celsius, this is a spontaneous process. What's important is that just because something's spontaneous doesn't mean that it's fast. Okay, that's a very important thing, is that the Haber process, great, this is a spontaneous thing. Nitrogen and hydrogen, you put them together, you'll get ammonia. But it's very, very slow. Okay, delta G has no reflection on rates of reactions. So what happens is, in order to make this reaction work in any meaningful way for an industrial process, they have to alter the conditions of the reaction. They add in catalysts, they change the temperature, they change the pressure, all kinds of things, in order to make it happen in a reasonable time frame. Right? I digress. Let's come back to our problem. So what we want to do is calculate delta G at 298 K, or 25 degrees Celsius, for non-standard conditions. So in our case, we want to say calculate delta G at 298 for a mixture of 1 atmosphere of N2 gas, 3 atmospheres of hydrogen gas, and 0.5 atmospheres of ammonia. Okay? So, non-standard conditions. So what I'm going to do is I'm going to calculate a Q. Right? So Q can be calculated for any point along the reaction process. So Q looks like an equilibrium expression. Pressure of nitrogen, pressure of N2 times the pressure of H2 cubed. Right? So remember, we're writing an equilibrium expression, so my squared comes from the coefficient of 2 in front of the ammonia in the equation. My cube comes from the coefficient of 3 in my expression there. So since I have those values, I can plug them in. Calculate a value for Q, and we end up with 9.3 times 10 to the minus 3. Okay? So now that I have Q, my delta G equation, delta G equals standard delta G plus RT natural log of Q, right? So I can just plug all my values into this expression. So delta G equals negative 33.3 kilojoules per mole plus 8.314 joules per mole Kelvin. Notice that my units don't match. So I've got kilojoules for the delta G standard, and I've got joules for my gas constant, so I'm going to convert that gas constant to kilojoules real quick. So 1 kilojoule is 1,000 joules times my temperature, that's the RT part, natural log of 9.3 times 10 to the minus 3. Okay, so here is my delta G naught plus R, convert to kilojoules here, here's my T, and here's my natural log of Q. Okay, and we come up with a delta G value at these conditions, which are non-standard, 44.9 kilojoules per mole. Okay. So let's figure out what is the value for standard delta G, or for delta G standard at equilibrium. Q equals K, delta G standard equals negative RT natural log of K. All right, so let's solve for K. Let's find out what is the equilibrium constant, knowing what the value for the standard delta G is. So solve for K if you know standard delta G, which we do. Right? So if I take my equation and rearrange it, I'm going to say natural log of K equals delta G over negative RT. And if I solve for K, equals E to the negative delta G over RT. Okay? So let's calculate K for the Haber process. Calculate K for the Haber process at 25 degrees C. Okay, so delta G standard we know is negative 33.3 kilojoules per mole. And we're going to convert that to joules just to make it easy because R is in joules. So that's negative 3.33 times 10 to the 4 joules per mole. Right, so now all I have to do is I have the delta G, I have the R, I have the T, I can just plug them straight into the equation. Equals E to the negative 3.33 times 10 to the 4 joules per mole divided by 8.314 joules per mole K times 298 K. And we find that K equals 7 times 10 to the 5. Right? Not a particularly large value for K, but that's what we've got. Okay, so there are a number of equations that you're going to want to have in your arsenal. I will, of course, provide you with all of the equations on the exam. I always do. And the exam is coming up on Wednesday. So hopefully everything is going to be a-okay with you all, and you're going to attend my office hours on Monday and ask lots of questions. And I hope that you enjoyed the video. Good luck and have fun.